Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we're going to introduce the concept of a KD tree. This is another spatial tree, so we're still talking about spatial data structures. And we saw in the last video that we could use a quad tree as a way of partitioning space so that we could do more efficient neighbor finding. We used a region-based quad tree. And the quad tree itself works for two-dimensional data, which is fine for this. It wasn't always balanced. That was one of its weaknesses. And also it didn't scale up to other dimensions. So the KD tree is a data structure that in many ways is designed to handle large dimensionality. In addition, we're going to be able to build it in such a way that the tree is always perfectly balanced. So the way the KD tree works, at a fundamental level, the KD tree is a binary tree. So if I put in two values here, I get them separated, and at each level we pick either to do a cut that is perpendicular to the x-axis or a cut that is perpendicular to the y-axis. So for example, if I put another dot there, so now I have these three dots here, and I have one cut at the top level. So the top, the root is basically split between these two children, and then on this side it's split between these two. If I were to add something over here, now the root is split right here, and this side, the left child is split this way, and the right child is split that way. Just like a normal binary tree, everything that's less goes to the left, everything that's greater goes to the right, with one difference, that it's not just left and right, it can also be up and down. It's all values that are less than something go to the first child, and everything that's greater than goes to the other child. And in this case, with the KD tree, we're not limited to just two dimensions like this. Because we're cutting along a dimension, it's very easy to say, well, let's cut along the z dimension instead. So how do we decide where to put these cuts? Once again, there are lots of ways to build KD trees. The way that I'm building them, all the data once again goes into the leaves. There's nothing that says that that's how it has to be done. You're perfectly allowed to build KD trees with data at every single cut, and which would actually make it very much like your standard BST. But we're going to put them down into the leaves, and at each time we have to keep track of which dimension the cut is along, what value the cut is along, and the children. And then also, if it's a leaf, we need data instead of children. So what does this look like if we have more? And then also there's the question of how do we decide? How do we decide what direction to cut in? How do we decide what value to cut? So for example, if I throw in 100 random dots here, you can see what this looks like. We throw in 100 more, we get that. One of the things to note, if I start adding in random dots here, the tree can change dramatically. And if I add a region of high density here, you can see what happens to the tree, that it actually, there's a lot of adjustment that goes on. The way that I'm building my tree here, I am putting the cut along the dimension that has the largest spread. So if I put my two dots that way, I get a cut there. If I put my two dots that way, I get my cut horizontal, so perpendicular to the y-axis. So I pick the dimension of my cut along the direction of largest spread. How do I pick the location of it? I take the median value. So for example, if I have a cut there, turns out that the cut for the root is now right along this point, because this point was now the median of the three data points. And then the next cut on this side, because it has two values on it, is halfway in between those two. So that's, and technically it didn't have to be halfway in between, it could have been on top of one of them. For graphical purposes on this tool, I've made it so it's halfway in between. But normally when I'm coding, I won't bother with that. What I want to make sure of is that half of the particles fall to the left side and half of the particles fall to the greater side. The advantage of that is once I do that, I am guaranteed that this tree is always balanced. Okay, so there's going to be an equal number of points off to the left and to the right for every single cut in this tree. So in other words, all of these data points that are in here are, and you'll notice that in this case, unlike the quad tree, every single square has a data point. inside of it. Technically not square, they're rectangles here. But every single one has a single data point because we don't cut unless there were two particles, and so we'd never get those empty nodes. Now some of these nodes are very large, like this one here. It has this point that's off in the corner, but it does have one point somewhere inside of it, and that is true for all of these. And at every single cut, so for example, this is our root cut right here. The number of points that is above that cut is equal to the number of points that's below that cut, and so the number of children up here is equal to the number of children down here. This tree is optimally balanced, and that's one of the advantages of the KD tree. Now, the challenge that we have is being able to build this without having it take a huge amount without it being, I guess, inefficient. So how do we get the median value efficiently? That's something that we're going to have to talk about, because the inefficient way to do it is to actually just sort all the values. So once I've decided that my cut goes in this dimension because the biggest spread is from there to there, to find the median, the slow way to do it is actually sort all the values and find it. But sorts are order in log n. And we want to build the entire tree in order in log n time. And it turns out if I do a sort at every level, I don't get in log n overall performance. So I have to do something that's only order n at each level. And it turns out there is a method for finding the median in order log n time. And so we will be introducing that as we write the code to actually build our KD trees, and we'll do that in the next video.